Hello students, welcome you all to the video lecture on architecture of 8086. So today we are going to discuss about the functional operations of 8086. So generally 8086 is nothing but a 16-bit microprocessor, meaning that it will operate with 16-bit data and it has 16-bit data bus, hence the name, it is a 16-bit microprocessor. So it is used to operate with 16-bit data, meaning that it can perform arithmetic operation, logical operations and all using a 16-bit data. So generally what do you mean by microprocessor? Microprocessor is an programmable integrated circuit which acts as a CPU of a computer or a embedded system. So generally it will accept the input and then it will operate on that input and it will produce the output. So it will accept the input, operate on that, and then that is we can say that it will process it and then it can produce the output. That is what your microprocessor will do. And then it is externally connected with the memory unit also. So it can either read the data or write the data to the memory. Either it can read from the memory or it can write the data to the memory. And generally the microprocessor will consist of arithmetic logic unit as what we have seen here, so that it can perform arithmetic and logical operations, and also it have control unit. So the control unit is responsible in order to control the overall operations whatever it is available within the unit. And then it will have some of your internal registers. So here we have 14 16-bit internal registers. So microprocessor 8086 is having 14 16-bit internal register. So that we will see one by one. So generally the block diagram or architecture of 8086 is splitted into two units. One is BIU, another one is EU. So BIU is the upper part within this dotted line, and then execution unit is the lower part of this dotted line. So what is BIU? BIU is bus interface unit, and then EU is execution unit. So the bus interface unit is used to connect to the outside world. That is, bus interface unit will connect the 8086 to the outside world. So in the outside world, in the sense it may be connected to the memory or input output devices. So the bus interface unit consists of a adder. So this sum indicates it is a adder and it is having the C bus, and then it is having instruction stream byte Q, and then it is having 5 16-bit registers. So 5 16-bit register in the sense ES. ES means it is extra segment. ES means extra segment, and then CS means code segment, and then SS means stack segment, and then DS means data segment, and then IP means instruction pointer. So these are all the 5 registers available in the upper part of the bus interface unit. So from the name itself, what your bus interface unit will do? The main purpose of your bus interface unit is it will fetch the instruction. So it will fetch the instruction from the memory. First it will fetch the instruction from the memory, and then it will transfer the instruction and it will store those instruction in this instruction byte queue. So this instruction byte queue, it is of 6 byte. So totally 6 byte of instruction it can store. So it will fetch the instruction from the memory, then through the bus it will transfer that and it will store that in the 6 byte instruction queue. Then this instruction one by one it will be moved to the execution unit, where it will be decoded and executed. So this unit will decode the instruction and then it will execute the instruction. So the bus interface unit will fetch the instruction, it will read the data from the memory, it can write the data to the memory, it can read the data to the data from the input output port, or it can write the data to the input output port, and then it will transfer the information through the buses to the instruction stream byte queue, and then the instruction stream byte queue will transfer those instructions one by one to the execution unit, where it will be decoded and executed by the execution unit. So this is the general description of this diagram. Let me see one by one what it is. So since the instruction stream byte queue is available here, the important concept here, that is pipelining, occurs in the 8086. So pipelining, what do you mean by pipelining? Means when one instruction is currently executed, parallelly the fetching operation of the next instruction will occur. For example, generally in the 8085 processor and all, we have fetching operation followed by decoding operation followed by execution operation. So if it fetches the first instruction, after fetching decoding will occur, after decoding execution will occur. Then it will move to the second instruction, fetch the second instruction, decode the second instruction, and then execute the second instruction. This will happen in 8085 microprocessor, where you don't have pipelining. But here, because of pipelining, what happened means, while fetching the instruction, first instruction only, the 8086 will become idle. But during the second fetching, automatically the decoding operation of first instruction will start, and then followed by the execution of the first instruction. So during the fetching of your third instruction, the decoding operation of first instruction and execution of your first instruction will be completed. So here the operation will happen parallelly. So for that, what is the necessary unit here in the processor? 8086 processor means it is instruction stream byte queue. Why? Because 6 instructions are fetched at a time and it is stored in the queue, and then these instructions are given one by one to the execution unit. Then again 6 instruction byte will be holded in the 6 byte queue. So first instruction, if it is given to the execution unit, automatically 7th instruction will be fetched and it will be stored in the instruction byte. So like that, the instruction queue is hold up to 6 byte of instruction, which makes the operation in a speedy manner. So when you see here, it takes nearly 6 cycles to execute your second instruction, right? But here what happens, so within the three cycles, the first instruction execution is completed, and also it fetches the second instruction and third instruction also. And then if we go for your fetching of your fourth instruction, parallelly the decoding of your second instruction will happen. Fetching of your fifth instruction means execution of the second instruction will happen here. And even we have instruction byte queue, where at a time 6 byte of instruction will be fetched. So one by one fetched instruction will be given to the execution unit, where it will be decoded and executed parallelly. And then the bus interface unit consists of 4 segment register. So let us discuss about the memory unit of 8086. So 8086 is having 20-bit address bus. So it can point out up to 1 MB of memory. So 1 MB of memory, it is having 4 segments, and each segment is of 64 KB size. So what are all the 4 segments means? One is code segment, another one is data segment, another one is stack segment, another one is extra segment. So we have totally 4 segments in the memory unit of 8086. 4 segment in the memory unit of 8086. So the code segment is used to store the code. We can say that is program or code is stored in the code segment, and data is stored in the data segment. And then in the stack segment, the loop instruction and then subroutine instruction. During the subroutine instruction, during the push and the pop operations, call and the return operations, what are all the instructions related to that, those instructions will be stored in the stack segment. And then if we have extra data, then extra data will be stored in the extra segment. So string related operations and all, it will be stored in the extra segment as well as the data segment. So destination data and all will be stored in the extra segment. Source data and all will be stored in the data segment. So like that we can store the data in the data segment, extra data in the extra segment, and then code in the code segment, and then subroutine operation related instructions and all will be stored in the stack segment. And then each segment, as I said, it is of 64 KB of memory. So totally 64 plus 64 plus 64 plus 64, only 256 KB of memory is used out of 1 MB of memory. And then each segment base is pointed out by registers. For example, this is the base of the code segment. This base is pointed out by CS register. This data segment base is pointed out by data segment register. The base address of your stack segment is pointed out by stack segment register. Similarly, the base of extra segment is pointed out by ES register, that is extra segment register. So in the block diagram we have ES, CS, SS, DS. These and all, it is registers. It is not segment, it is registers. These registers point out to the base of a particular segment. Code segment is pointed out by code segment register, data segment is pointed out by data segment register, stack segment is pointed out by stack segment register, extra segment is pointed out by extra segment register, right? And then we have actually physical address and logical address. So physical address in the sense, it is actually calculated by 8086 itself. So generally the physical address, it is of 20 bit, but our registers and all, it is of 16 bit. So logical addresses are stored in the 16 bit register, but automatically the 20 bit address will be calculated by the 8086. So how your physical address is calculated? It is calculated by, physical address is mentioned as PA. It is calculated by segment register into 10 plus offset address. It is calculated by segment register into 10 plus offset address. So segment register, as what we have discussed now, what are the segment register available? 4 segment registers are available: CS, DS, ES and SS. Okay. Offset address, similarly we require other registers. So offset address, it may be IP, it may be IP, it may be SP, it may be BP, it may be SI, it may be BI, it may be BX register also, right? So the offset address is given by these registers. So those registers, actually here one of the offset address, that is instruction pointer, is given. So one offset address is given by instruction pointer, other offset address is given by other register, namely stack pointer, base pointer, source index, destination index, which is available in the execution unit. So before explaining each and everything, first let us see what do you mean by offset address and how we are calculating the physical address. So this instruction pointer is offset address for the code segment. That is, it will point out the offset address of the next instruction to be executed. So it is always related to the code segment. So for the code segment, whenever we are saying that segment register is a CS register, I can say that for the code segment, the offset address is always IP. So whenever I am using CS here, definitely the offset address will be IP register. So similarly for the data segment. So for the data segment, I can use any of your register, SP, BP, SI. Here it is not BI, it is DI. SP, BP, SI, DI or BX. Any register I can use for your data segment. And then stack segment, particularly I can use your SP or BP. Stack pointer register or base pointer register. And then extra segment, the offset is given by DI. And then if it is string operation, then the data segment, particularly it will use your SI register as offset. Okay, so data segment generally we will use offset address as BX also, BP also, SP also, SI also, DI also. Whatever may be, we can use it as offset address. But particularly if we are going for a string operation, then data segment is related with SI, extra segment is related with DI. Particularly if it is stack related operation, stack segment will be using the offset address as SP and BP. Okay, so IP means instruction pointer. Instruction pointer which will point to the address of the offset address of the next instruction to be executed. So currently one instruction will be executed by 8086. The next instruction offset address will be carried over by instruction pointer. Okay, and then so coming to the bus interface unit, we have these 4 segment register and IP. So these and all segment register, this is your instruction pointer which is nothing but your offset address, and then we have bus interface unit which is connected with the instruction byte queue. What is the purpose of the instruction byte queue? It is used to speed up the execution operation which will happen next. So it will support pipelining operation. Then what is the requirement of this sum? So this sum is nothing but the adder which is used to calculate your physical address. As I said, this unit only, it is calculating the physical address. So physical address, as I said, we have to use segment register, that will be multiplied by 10 and then plus offset address will be added and then physical address will be calculated. So this operation is done by the bus interface unit. So for example, if my CS value is 2000, IP value is 1000, then my physical address will be 2000 into 10 plus 1000. So what happens? It will be 20,000 plus 1000. So it will be 21,000. So like this we can calculate your physical address. But we are doing this in the manual manner, but automatically always the 8086 will do it by itself. So this physical address calculation will be done by the 8086. It is not necessary for us to do. Okay. So for doing that only, we have this bus interface unit. So I hope you have understood about your bus interface unit. So next we will move on to the execution unit. So in the execution unit, as I said, the main thing is your decoding operation and executing operation. And then we have control system, and then ALU, arithmetic logic unit, is responsible for the execution, and control system is used to control all the internal operation within the 8086. and then we have execution unit, which is used to decode as well as execute. So decode in the sense it will translate the instruction into set of series of actions what it has to do. For example, if it is receiving the instruction like move, so here I have move instruction. Okay, move ax comma bx means this data whatever available in the bx register will be moved to ax register. So what is the meaning of this instruction will be given by the decoder to the execution unit. So this instruction whatever it is fetching will be given to the execution unit, and what is the meaning of that instruction that will be done by your decoder. So decoder is one which will decode the instruction and it will translate that instruction into series of action. What it has to do? It has to move the data from bx to ax. Like that it will give the series of action what the 8086 has to do. Then after getting the series of action from the decoder, automatically your 8086 will execute that operation. For execution generally it requires your arithmetic and logic unit, because arithmetic and logic unit will do all your arithmetic operation and logical operation. Okay, and then so here it is for fetching, this unit is for fetching, and then the below unit is for decoding and execution. And then we have some internal registers here. So AX, BX, CX and DX we have. So these register as a 16-bit register, I can name it as AX, BX, CX and DX, but it has been splitted into two 8 bits. One is AH, AL, BH, BL, CH, CL, DH, DL. So here AH means A register high byte, AL means A register low byte, BH means B register high byte, B register low byte, C register high byte, C register low byte, D register high byte, D register low byte. So again, when we see your registers, so we have general purpose registers. So totally we have 4 registers, general purpose register. As I said, it is AX. So AX, it is nothing but a 16-bit register. It is splitted into two 8 bits, upper 8 bit and lower 8 bit. Lower 8 bit alone we can say that it is AL, upper 8 bit alone we can say that it is AH. So this part is AH, this part is AL, and the whole 16 bit is nothing but AX register. So similarly it is for BX, CX and DX. Either we can use it as a 16-bit register directly, or we can split into 8-bit register and we can use it. And then so coming to the AX register, it is actually named as accumulator. So accumulator in the sense all the result, whenever we are doing some arithmetic operation, logical operation, the result will be always stored in the AX register. Hence AX register is also called as accumulator. And then again, in most of the operation, one of the operand is always stored in the accumulator. For example, when we see addition operation 3 plus 2 which is equal to 5. So one operand, one data, whatever the data available, one data most probably it will be stored in the AX register. So another data it may get from other registers also, it may be from memory location also, or it may be from input output devices also. So one operand always it will be from AX register, and after doing the operation also result will be stored in the AX register. Okay, so this second operand it may be from BX register, it may be from CX register, it may be from DX register, or it may be from any memory locations available, or it may be from input output devices also, second operand. Okay, and then so coming to the next register, that is BX register. So BX register again it can also use to store the second operand. So maximum instruction we will use BX register to store your second operand, and it is also called as base register. So base register in the sense it is used to store the offset address. It is used to store the offset address. As we have already seen the physical address calculation, for that we require one segment register, one offset address. So one offset address is also provided by BX register. So this BX register particularly it is used in based addressing mode. So we will see addressing mode later. In the based addressing mode and all, the offset address is generally given by BX register. And then CX register, it can be used to, it can be act as a counter. That is, it is used to store the count during the multi-iterative operation. So whenever we need to do repetitive action, then those things, repetitive action, how many times it has to do, that count I can store in the CX register. So for example, if I want to blink an LED 5 times, okay, so if I want to blink an LED 5 times, okay, so first time it is blinking, after that automatically CX register will be, the count will be stored in the CX. After blinking one time, the count will be reduced to 4. So again the blinking, if it happens for second time, the count will be reduced to 3. So like that 5 times whenever the blinking is over, CX register will be automatically reduced to 0. So whenever I have repetitive operation, the count you can store in the CX register, hence it is also called as counter register. And then DX register, particularly it is used during the input output operation, and it is also useful in division and multiplication operation. So when I'm going for input output operation and division and multiplication operation, then DX register is useful. For example, whenever I have multiplication operation, when we multiply 16 bit into 16 bit, 16 bit into 16 bit, we will get the result as 32 bit. So in that case, the lower 16 bit and then we have upper 16 bit. The lower 16 bit will be stored in the AX register. Why? Because always result will be stored in the accumulator. The upper 16 bit will be stored in the DX register by default. So during the multiplication operation, whenever we are multiplying 16 bit into 16 bit, the lower 16 bit will be stored in AX, upper 16 bit will be stored in the DX register. Similarly, during the division operation, we have two things after the operation, that is, one is quotient, one is remainder. We will get quotient and remainder. By default, quotient will be stored in your AX register, remainder will be stored in the DX register. So during the multiplication and division, definitely we require the DX register. So coming to the block diagram, so we have seen these general purpose register. Then we have pointer registers and index register. So SP and VP are nothing but pointer register. One is SP means stack pointer. So it will point out to the stack. Another thing, BP is nothing but base pointer. So these two pointers are used along with the stack segment. So whenever we are doing the stack related operation, then we require the physical address of the stack segment. During the physical address calculation, we require SS register, stack segment register into 10 plus your offset. So this offset is given by SPR BP register, as I said before. So if it is a stack segment, then the physical address of the stack segment is obtained by stack segment register into 10 plus offset address. This offset address is given by these two register. So similarly, I have two more register called index register. So index register in the sense, SI is source index, DI is destination index. Source index and destination index. So source index means whenever we are going for string operations and all. Okay. So we have source as well as destination. That is when we are moving the string called ABC from source to the destination. When we are copying the string from source to the destination, then this source address is pointed out by DS and SI. This destination is pointed out by ES and DI. So meaning that here the physical address is calculated by DS into 10 plus SI, and then destination physical address is calculated by ES into 10 plus DI. So like this, whenever we are going for string related operations, particularly string related operations, in these operations, in order to point out the source address, we require data segment into 10 plus SI. So SI here will act as a offset address, and then for destination, DI will act as a offset address, right? So we have discussed about this unit, and already we have discussed about the arithmetic logic unit, which will do the arithmetic operation and logical operation. So arithmetic operation in the sense addition, subtraction, multiplication and division. Logical operation in the sense AND or XOR operations and all. So these things will be done by your ALU. And then as I said, for each and every operation we require the operands. So operands, it may be either the data, or it may be the registers, or it may be the memory locations. And then all these operations will affect the status of the flags. And inside the flag register we have status flag as well as the control flag. So let us discuss what is your flag register. So in the flag register, it is again a 16-bit register. So in that only 9 active flags are there. So 6 flags are status flag, 3 flags are control flags. So status flag in the sense, for example, after doing the result, if the result is a 0, okay, that is you are doing the operation, addition operation. After doing the addition operation, for example 0 plus 0, okay, what is your result? It is 0. If your result is a 0, then this 0 flag will be affected. That is 0 flag will become 1. It will set to 1. If result is not 0, then it will become 0. 0 flag will be 0 whenever result is not 0. So whenever result is a 0, then it will set to 1. So similarly, after doing the operation, if your result is having even number of ones, for example, if your answer is a 4, okay, so if I have 8 bits, so 0, 0, 1, 0, 0 is your 4, okay. So if I have 8-bit data, right, and then the other upper 8 bits and all, it is 0 only. So here all the 8 bits and all 0. So for example, here also 0. Upper 8 bits are 0 and lower 8 bits we have like this, okay. So totally it is nothing but a 0, 4 value. Why? Because here it is 0, 1, 0, 0. So how many number of ones are there? It is odd number of 1. Only 1 is there. 1, 1 is there. So it is odd number of 1. So if suppose I have even number of 1, okay, like this 1, 0, 1. If it is 5, 1, 0, 1, even number of 1, then the parity flag will be set to 1. So even number of 1 means parity flag is set to 1. PF value will become 1. Odd number of 1 means parity flag will become 0. So according to the result, it will affect your flag register. That is what I am trying to tell. And then auxiliary carry. Auxiliary carry means if you are doing some operation, if you are getting, for example, if you are taking the 4 bits, other bits and all, here it is available, okay. So if you are doing some operation, if you are getting the carry from fourth bit, if you are getting the carry from fourth bit, this is D0, this is D1, this is D2, this is D3. If you are getting the carry from fourth bit or D third bit, then auxiliary carry flag will be set to 1. So if you are doing some addition operation, for example, here also you have 1, here also you have 1. If you are doing the addition operation, here it is 0, 0, 0. 1 plus 1 is what? 0, and then followed by you have 1 carry. So if you are having a carry from the fourth bit, then auxiliary carry flag will be set to 1. Will be set to 1. If you are not getting any carry, auxiliary carry flag will be 0. So similarly, if you are getting the carry after the addition of two datas, if you are getting the carry from last bit, that is D15 to D0 you have, okay. So if you are getting the carry from the MSB, most significant bit, then the carry flag will become 1. If you are not getting any carry out of D15th bit, then carry flag will become 0. Okay, and then sign flag. Sign flag in the sense, suppose if you are taking this number itself, after doing the addition operation or logical operation, if your result is like this, you have to see your D15th bit, that is your last bit. If your last bit is a 0, then sign flag is 0. If your last bit is a 1, then sign flag it is equal to 1. So meaning that the most significant bit, whenever it is a 0, it is positive number. The most significant bit, whenever it is 1, it is negative number. Hence it affects the sign. Okay. So negative number means this bit will be 1. So sign flag will be 1. Positive number means this bit will be 0. That is most significant bit will be 0. Then I'll be getting SF equal to 0. Right? And then if you are doing some addition operation and if you are getting the result, addition or multiplication, whatever it may be, if you are getting the result out of range, that is you cannot store that data at all, okay, within the 16 bit, then I can say that out of range means overflow flag will be set to 1. So if you are getting the out of range of your result, which I cannot store in a register, then overflow flag will be set to 1. So parity means you have to find out the result, whether it is having even number of ones. Even number of 1 means it will become 1. Auxiliary carry means if you are getting the carry from fourth bit, then I can say auxiliary carry is equal to 1. Carry means if you are getting the carry from 16th bit, that is D15th bit, then this bit will become 1. Sign flag means 0 means positive, 1 means negative, so it will become 1 whenever it is negative. If it is out of range, then overflow flag is equal to 1. Okay. So in more detail, if you want, in the next video flag register will be explained, there you can see. And then interrupt flag. Interrupt flag means you have a INTR pin in the pin diagram of 8086. Using that, some interrupts will arrive. So whenever that interrupt is coming, 8086 have to decide whether it has to accept the interrupt or ignore the interrupt. So when interrupt flag is equal to 1, it will accept the interrupt and it will execute the interrupt. And then if this bit is a 0, it will ignore the interrupt. So for example, any circular is coming in your classroom. If you are ready to accept and read the circular, then IF is nothing but interrupt enable flag. You are accepting. Accepting means IF is equal to 1. So if you are not ready to receive, if you are not ready to accept the interrupt, then interrupt flag become 0. And then trap flag. Trap flag means, so whenever TF flag is equal to 1, meaning that the processor will go for single step execution. That is, it will execute the instruction step by step. So after, if you have multiple instruction, okay, 3 or 4 instruction, after executing the first instruction, the 8086 will pass, and then it will give the result. What is the status of your register, what is the status of your memory locations, all those things will be observed by the programmer. And then again the programmer, if it is ready, then he will go for the next instruction execution. So one by one instruction will be executed and result will be available for the programmer. In that way, if you are doing some execution, then trap flag is equal to 1. So generally trap flag, why we are using means, in order to debug your code. Suppose if you are finding some error in your code, okay, so the whole set of program, after it is executed, you cannot find where you have a bug in your program. So we are going for single step execution. So after each and every instruction, if you are able to know the result, then you can easily find out which instruction is fault. So in that case, you can make your TF is equal to 1, then it will go for single step execution. When TF is equal to 0, it will do the whole program execution. And then direction flag. So suppose if you are transferring the data, that is your string byte and all. So how we are going to transfer your data, whether from lower address to higher address or higher address to lower address, that is decided by the direction flag. So when by default DF is equal to 0, so always we will go from lower address to higher address, lower address to higher address execution. So whenever DF is equal to 1, the reverse will happen. Higher address to lower address will happen. So if you are having your string, right, A, B, C, D. Okay, so this is your address 2000, this is your address 2001, this is your address 2002, this is your address 2003. So if your DF direction flag is equal to 0, then it will take A first, followed by B, then C, then D. If DF is equal to 1, if DS is equal to 1, first it will take from higher address. It will take D, followed by C, followed by B, followed by A. So auto increment will happen. Auto increment will happen when DF is equal to 0. Auto decrement will happen when DF is equal to 1. Hence it is called direction flag, in which way you are going to take your value during the string operations. So coming to the block diagram, right? So everything we have discussed. So the main thing is bus interface unit will connect to the outside world, and it is mainly used for fetching operation, as well as it is used to transfer your data through the buses, and then it is having the instruction stream byte queue, which will speed up the operation of the execution, and also it supports the pipelining, and also it is important to calculate your physical address, and we have all the segment register, and additionally we have your IP register. And then here in the execution unit, the control system is one which will control all the internal operation, and this execution unit is important for decoding and executing. Decoding means it will translate your instruction into set of series of action. Execution means it will do the operation. And these are all your general purpose register. These register, pointer register, index register, acts as the offset address. And then arithmetic logic unit perform arithmetic and logical operations. Flag will get affected after the operations. So totally we have 9 active flags. Thank you. Thanks for watching.